Alright, hello and welcome to the final review. Let us get started and review as much as possible. So I just have a bunch of topics that I'm going to go through, and I have a bunch of examples. So let's get started. And please yell at me, come to office hours, or yell at me on Discord if you have any questions about this stuff, or if there's something that I missed that you'd like me to talk about. We can talk about it there. Alright, so let's start with sequences, because that'll bring us into induction land, right? So there are two standard kinds of sequences that you can build very easily. You can have arithmetic sequences, which keep on either increasing or decreasing by a common factor. If only I could count by fours. So adding 4 every time, for example, is an arithmetic sequence because the common difference between each element of those sequences is 4, positive 4. So it's going to get bigger every time. It's always plus 4. That is an arithmetic sequence. And any sequence in general can be talked about using the elements of the sequence. So which element of the sequence is this? Maybe this is a sequence called S, and this 4 would be element number 0, right? This 8 would be element number 1, 12 would be element number 2, and this is S3, so on and so forth. All right? So that is arithmetic sequences. Geometric sequences are pretty much exactly the same, but instead of a common difference, there's like a common factor. So you multiply. Or if it's a fraction, it's technically division, right? So maybe 1, 2, 4, 8, 16, 32, and onwards. That's a geometric sequence because it keeps getting bigger by a factor of 2 each time from the previous element. Right? So that's a geometric sequence. And when you have sequences, you can say, you can classify them into decreasing, non-increasing, non-decreasing, and increasing. Okay? So let's give examples of all of those now. So a decreasing sequence is always getting smaller with each successive element. So like the sequence 5, 4, 3, 2, 1, that's totally a decreasing sequence because it's always getting smaller, right? It's decreasing. Dictionary definition of decreasing. A non-increasing sequence is slightly different from a strictly decreasing sequence. This is a sequence that is not decreasing, because it can stay at 5 for a split second, but it's also not ever getting bigger, so we say it's non-increasing, okay? So it can, like, stick around at some numbers for a little while. This is a non-increasing sequence. It's getting smaller or staying the same. 3, 2, 1. So this is a non-increasing sequence. Here is an example of a non-decreasing sequence. So it can stay at, like, 1, 1, 1, 2, 2, 3, 4, 5. It's getting bigger or staying the same. So it's definitely not decreasing, but it's not strictly increasing either. Okay, see the difference there? And then finally, increasing is the opposite of decreasing. It's always getting bigger each time. It's never staying the same. Okay, so those are some finite sequences that can be classified in those 4 ways. All right, and then usually you make a sequence with some kind of formula. If it's not recursive or using like a recurrence, it's using some kind of variable, okay, a lot of the time. So, for example, here is a sequence defined as every element of the sequence, an, is equal to n squared minus 4n, and it starts at 1. So what is a1, what is a2, what is a3? You can calculate all these things, right? So it's a1 is 1 squared minus 4 times 1, so that's negative 3. A2 is 2 squared, so 4 minus 4 times 2, so 8, so that's negative 4. A3 is, let's see, 3 squared, so that's 9 minus 4 times 3 is 12, that's negative 3 again, yeah, oops. What's A4? That is 4 squared, so 16 minus 4 times 4, wait a second. Is that what I think it is? So, yeah, 4 times 4 is 16 minus 4 times 4. I believe it's 0. Yeah? 0. A5 is 25 minus 4 times 5, so that's 5. A6 is 36 minus 4 times 6, which is 24. So 36 minus 24 is 12. I think this is correct. And so then you can go and classify what kind of sequence is this. I have a feeling it's going to keep getting bigger after this point, but it kind of like bounced around. It's neither increasing, right, because it's getting smaller here. It's not it's not decreasing either, because here it is getting bigger. So it's kind of none of the above, right? So that's a fun little sequence there. And so that's an easy way to define a sequence is in terms of which element you are, which element you're looking at in that sequence. Okay? You can also do it using recurrences, and we like that. So let's do the Fibonacci sequence using a recurrence, which is just defining a sequence in terms of itself, in terms of previous elements. So the Fibonacci sequence, let's call that sequence F, and we can start it off, right? The first number, the 0th number in the Fibonacci sequence is, we can define it to be 0. The first number, the element number 1 in the Fibonacci sequence, so f of 1, is the number 1. And then after that, f of any number for n greater than or equal to 2, any index into the sequence, is equal to f of n minus 1 plus f of n minus 2, right? Those previous two elements, add them together, and you have then made the Fibonacci sequence, okay? And so an easy question for me to ask you would be something like this. What are the first 6 terms of this sequence, given these starting conditions and this recurrence relation? So very easy to write the first 2 terms, right? C1, C2 is, we got 4, we got 5, and then we need C3, C4, C5, and C6. What in the world are they? So C3, for example, is C2 times C1. So it's multiplying the 2 previous elements, it seems. So what is 4 times 5? That is 20. What is 20 times 5? So C4 is equal to C3 times C2, right? The 2 previous elements multiplied together. And that's going to be 100. And this is going to be, what, 2,000? And this is going to be how many zeros? So we start with 2,000 and add 2 more zeros, right? So 200,000? So those are the first 6 terms, and that's how you look at it, and that's how you think about it. Okay, so it's easy to define a lot of things in terms of previous elements. Maybe not just the one before it, but maybe 2 before it as well. Okay, so that's an example of recurrences to define sequences. What else did we talk about? We also talked about summations, right? So here's my fun example. Jeff Bezos makes this much money per second. It's probably more now because I calculated that last year. So let's use a summation to represent how much money Jeff makes in a single day, some astronomical amount. So remember that a summation is all about that Greek capital sigma, S for sum, right? It's their letter S. And you have to give a starting condition down here. It's like a for loop in math, right? You got to have your ending condition up here, and then you have your just your expression that you want to calculate each term and add into the total. That goes to the right of the summation sign, that big sigma. So, for example, let's talk about how much money Jeff Bezos makes in a day. Or is it Bezos? I can't remember. We have to add up every second, right? So he makes that much money per second, but how many seconds are there in a day? Well, there are, well, we can number them. Here's the first second in the day, and the last second in the day is, well, 60 times 24, right? 60 seconds per minute, 60 minutes in an hour, 24 hours in a day. So that's how many seconds there are. So go up from second number 1 to second number whatever this is, and every time you have a new I value, keep adding 3,715 each time. Yeah? So if you add 3,715 this many times, you will end up with how much money Jeff Bezos makes in a day. So, good for him. So that's my first example. Here's another slightly more involved example. Let's try to represent the sum of the first n elements of this kind of form. So 2 times 13 plus 3 times 23 plus 4 times 33. What would be the next one? Looks like the pattern is 5 times 43, right? Then the next one would be 6 times 53. You see the pattern now? So it seems like we have that going on. And we can pick our starting value because it's always a summation. We get to control where we start. Like, does I start at 0? Does J start at 1? It really doesn't matter. So let's just start our I at 1. It might make it easier. So let's say that this is element number 1. So when I is 1, we want to calculate this. When I is 2, we want to calculate this. When I is 3, we want to calculate this. And we would like to sum the first n elements, right? So starting at 1, going to n, we need to do some stuff. We need to multiply 2 things, right? We need to get 2 from 1, right? Likewise, we need to get 3 from 2 and 4 from 3. It's always one more. You see that? So it's always I plus 1. That'll give me my 2 or my 3 or my 4. And I want to multiply that by 13 when I is 1, 23 when I is 2. And there's a pattern going on there. It's always, well, you start with 3, right? And then you add, it looks like 10 times I. 10 times 1 is 20, 10 times 2 is, 10 times 1 is 10, 10 times 2 is 20, keep on adding that 3. 10 times 3 is 30, and then we just keep adding the 3. So it looks like it's I times 10 plus 3. Those are the two numbers that I want to add, to multiply to each other, to add into my sum. Does that make sense? So this would be I equals 5. Does that correctly calculate here? So when I is 5, we're going to get 5 plus 1, so 6 times, and then 5 times 10, so 50, plus 3, that's 53. So those are the two numbers we want to multiply for that element of the sequence. And so if we want to sum the first n elements of the sequence, it's, well, go from I equals 1 to I equals n, inclusive. Okay? So that's summations in a nutshell all over again. And that brings us finally to induction. That's where we were going, learning about all this kind of stuff, right? Let's talk about induction now. So the idea was always, when you're doing an induction, you have a predicate. You have a predicate that you're trying to prove, like P of n, and you're trying to prove it for every single n, every single number starting from a certain one. Usually it's like starting from 0, and so it's like for every natural number, P of n is true. That's what we would like to prove. Let's get rid of the red mark, sorry. Or maybe for all n greater than or equal to 1, or all n greater than or equal to 2, P of n is true. But it's always, there's a starting point, and you want to prove that P of n is true for all n's after that, right? So P of 0 is true, and P of 1 is true, and P of 2 is true, on and on and on until the end of time. And so to do that, the standard way of doing that is through induction. So you have the base case, which starts you off, it's like, I know how to prove the smallest piece of this predicate. I know that P of 0 is true, and here's how. And then you use your inductive step, which is kind of like the meat of the proof. The inductive step shows, or it is a proof of the fact that for every k, if you give me P of k, if P of k is true, then I'm able to construct a proof that P of k plus 1 is true. Okay? That's what the inductive step shows you. And then every time you're proving this, right, it's for all quantified proof, it's always of this form, which means you get to use direct proof. So you assume this, prove that. And so the thing that you're assuming, because this is a special kind of proof called a proof by induction, we say that the thing we're assuming in our inductive step is our inductive hypothesis. Okay? So we give it a fancy name. That's just P of k, though. You assume P of k is true, prove that P of k plus 1 is true. Just your standard direct proof. Alright, so let me prove to you that that classic formula that the sum of all the numbers from 1 to n is equal to n plus 1 times n over 2. And so we'll prove this by induction. And that means we need a predicate that we want to prove for all n. And what do you know? Here is a predicate defined using n, right? The sum of all the numbers from 1 to n is equal to this. That is a statement. That's a true or false statement. It just needs a p. Right? So P of n, let's define it to be this in terms of n. So that's what we want to show is true for every n. It's true if n is 1. It's true if n is 2. If n is 3. Yeah? So let's prove it. Proof. So the base case is that, well, we have to show P of the smallest thing is true. And I think the smallest thing is the sum of all the numbers from 1 to 1, right? So P of 1, I would say. P of 1. And that is, we need to show that the sum of all the numbers from 1 to 1, I'll use summation notation, sum of all the numbers from 1 to 1 of I, because I ranges over every number, we need to show that that is equal to 1. And, okay, that's just, this expands to 1 itself. Yeah, that's totally equal to 1. So we've proven the base case. That's the easy part. And now we do the inductive step. Okay? So let me write it out, and then we'll do it on the next slide, because we need space. So the inductive step is like this. So we assume that P of k is true, and use that to prove that P of k plus 1 is true. So we assume P of k is true. And what is P of k? Well, it's just this predicate, replace n with k. Assume that 1 plus 2 plus dot 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 all the way to k is equal to k plus 1 times k over 2. Yeah? So that's our inductive hypothesis that we get to use, and what we need to show, right, is P of k plus 1. It's a direct proof. We need to show that P of k plus 1 is true, which is the idea that 1 plus 2 plus dot 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 all the way to, including k, but up to k plus 1, right, is equal to, well, plug k plus 1 in for n, it's k plus 2 now. K plus 2 times k plus 1 over 2 again. Okay? So that's our inductive step, and we need to go and use our inductive hypothesis to prove that what we expect is really happening. So let's take that, paste it up in here, and let's go off and prove it. Okay. So we want to use this idea. We get to assume that if you ever see this, you can replace it with this. That is our inductive hypothesis. Do we see that anywhere? Oh man, what is this? What is 1 plus 2 plus all the way to k plus 1, but 1 plus 2 all the way to k first, and then 1 extra k plus 1, yeah? That's the idea. So, with that in mind, we can replace this with the right-hand side of our inductive hypothesis. So let's do that, because we can use that fact. What happens when we do that? So, we started here. We're trying to show this side of the equation is equal to this side of the equation. So let's start with the left. 1 plus 2 plus dot 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 plus k plus 1 is equal to, by the inductive hypothesis, 2, well, replace this with this. So it's k plus 1 times k. We get to assume that this is true for a smaller value of our predicate, for the next smaller value. And then we still have the k plus 1 left over, right? So that's what we have now. And we can actually bring this all under the same fraction if we make common denominators, right? So this is still k plus 1 times k over 2. And then this one is, if you want to give a 2 as the denominator, you have to put a 2 on top too, right? 2 times k plus 1 over 2. And now we have a common denominator that we can put all together. And so let's expand the top as well, just to save us some time. So this is k squared plus k plus 2k plus 2. And this is all over 2, right? Because we found that common denominator. And so combining the terms that are alike, we end up with this. And if you remember your FOIL rule, this expands, or it factors, if you do it in reverse, to k plus 2 times k plus 1 over 2. And what do you know? That is exactly what we needed to show. So we have proven for any n, QED for the inductive step, we've proven that for any n, the sum of all the numbers from 1 to n is, it has a closed form. It's equal to n plus 1 times n over 2. And that is a fun example of induction. Okay? Hopefully that's bringing it all back to you. Let's keep on trucking now with recursive set definitions, because you can define not just sequences in a inductive way, in a recurrence-based way, an inductive way, a recursive way, these all have similar roots. You can define entire sets with recursive rules. All right? So here's an example that was similar to something that you had in your homework. So let's say that we're defining a set called S, and it's an S of a set of strings over the alphabet A, B. So all the things, all the words that we make of strings that we put in our set only have the letters A and B in them. Okay? Potentially the empty string is included as well. So you can define a set of strings by saying, okay, base case, here are things that I immediately know are in my set S, and then recursively, you can say, you can pick something out of your existing set and build up bigger things. So if you find X in S, then take it out for a second, plop an A at the end, I claim that's also an S. Right? My rule says that's also going to be an S. You can also stick an AB at the end. That's also going to be an S. All right? And so our job is to list all the strings of length at most 3 in the set S. So let's figure this out. So the idea is this set is an infinite set, but it's being defined slowly but surely through these rules. So the set S, it's like a big cloud, right? And it starts out holding 2 things for sure. The empty string lambda, and then the string with just b in it, okay? And so that's the base case. We know that the set contains these elements, and then we run the recursive rule. If we have something in S, then we can also have that thing with an A at the end, or with a AB at the end. That's also in S. So for example, let's take lambda out of S. Lambda could be an X, that's in S. That means that lambda A is also in S. Lambda AB is also in S. And when you have lambdas, those go away when you have actual characters, right? That's the empty string concatenated. So that means A and AB are also going to be in S. You see that? So that was through lambda. And then now let's do the same rule for B. So let's take out the B, and B can be our X. So that means that BA is an S. BAB is also an S. We're defining it this way. BA. BAB. Yeah? What else? So notice that these recursive rules always add at least 1 character. So it's not useful for me to run the recursive rule with BAB, because I only want to get at the strings of length at most 3. Okay? So I did it with B and lambda already. Let's do it with A. So that means AA is an S. AAB is an S. Yeah? Let's do it with AB. That means ABA is an S. And ABAB is also an S. Yay. So again, I don't have to do this one anymore. But there's another, we made another string of length 3. Cool. Let's do it for BA. That means that BAA is an S. BAA. And then BAAB is also an S. BAAB. Alright? Let's do it for this one. AA. That means AAA is an S. And AAAB is also an S. Okay? So I think these are things that I've built up so far. If I run the rules for anything that I haven't looked at yet, it'll just make bigger strings. So I think my answers then are going to be these. Strings of length at most 3. This one, this one, this one, this one, this one, and that looks to be all of them. Are there any duplicates? I believe none of these are all different from each other, right? So yeah, those are the 5 strings of length 3, or at most 3, I guess, in S. So I guess if we include at most, that means this one's included, this one, this one, this one, this one, also the empty string, all of those, but not the length 4 ones, so we don't want to go any bigger than that. Okay? So that is recursive set definitions. You're using these recursive rules, it's like a recursive function, to build up strings, to say what is in this set. And it doesn't just have to be strings, it could be anything. You can build up any mathematical thing, put it in a set. Okay, so that's that example, and let's keep on trucking. So, for example, it seems like some things are not in S. BBB, that is not in the set S, is it? So there are some things that are not there, and so this is an interesting rule, right? It's not just going to go and make every string, it's going to make only some special strings. So that's fun to think about. And so recursive set definitions bring us naturally to just recursive algorithms in general. We want to build up an answer to a recursive problem using our computer science programming knowledge, right? So there's a jump from this that have similar rules to actual programs. And let's go there. Let's make that jump. My standard example of a recursive algorithm is factorial. And so we noticed, for example, that we had a base case. 0 factorial is defined to be 1, you can immediately stop. And then also, if you try some examples, you notice that n factorial is equal to n times n minus 1 factorial. You find the smaller factorial. Yeah? And so that leads you, naturally, to a recursive algorithm for factorial. So int fact, if we do it in C++, the fact of some number n factorial, is, well, if n is 0, then you return, that's your base case, you return 1, else you return n times fact, right? You're calling yourself on a smaller value, fact of n minus 1. And that's your factorial function. So, what can we do here? We can find first the recurrence relation for the number of operations, right? Recurrence relation, let's call it t. T of n for the number of operations for an input of size n. Because, for example, if we're doing the factorial of 5, you have to essentially loop 5 times. If we're doing the factorial of 100, you have to essentially loop 100 times, but using the stack because it's recursive, right? So you have more stuff to do, and so it's natural to want to know how much stuff are we really doing. So let's use this to find the recurrence relation, use our implementation. Let's analyze it. So t of n, the number of operations when fact is called on n, is equal to, well, we usually only consider the recursive case, right? For this kind of relation, we say, okay, t of n is equal to, well, we have to make a recursive call in the recursive case, so it's, well, however much time it takes to run the function with n minus 1. So it's a recurrence relation because it's defined in terms of itself, so that's cool to do. That's the recursive call. That's the amount of time it takes to do the recursive call. Plus, how much extra stuff do we need to do? We need to multiply that result by our n and also return it. So those are constant things to do. I hope that makes sense. That's just constant work after you make the recursive call. So theta of 1 stuff to do after we've made that recursive call. You got to do the times, you got to return. That's just 2 operations. So that's totally constant time. Okay? And now the question is, can we solve this? Can we solve this using the master theorem, for example? And so I just so happen to have the master theorem slides right here to see if this works. Can we solve it with the master theorem? Does our t of n look like this? T of n equals something times another t, so there's, our a would be 1, we have an o of something, n to the 0, right? But, sadly, this inner bit does not look like n minus 1. Darn. So that means we cannot use the master theorem. No. Sad day. Okay, so we can't do it, unfortunately, so there's got to be another way that we can figure out the solution to this recurrence relation. And really, the easy way to do it is to use trees. So just draw the way that this t of n is going to unwind itself. So t of n is equal to, well, at this call, it's going to be constant work, plus you got to go off and do t of n minus 1 work, right? Which itself has constant work, right? And then it goes off and it adds that amount of work to a call to t of n minus 2, right? Which does constant work at its level, plus all the work that you do at t of n minus 3. All the way downwards, again constant, all the way down to the last call, which is the base case, which is going to be constant work. So it looks like every time you use the t, and you have about n t's, right, n calls to t and uses of the recurrence relation, you have constant work at each level. So the question is, how high is this little tree of unwinding of the recurrence relation? It's n high. So it's n times constant work at each level, so that gives us theta of n. It is a linear time algorithm, which makes sense. It's just going to go down to 0 and keep on multiplying all the numbers between n and 0, or n and 1. Yeah? So that allows us to solve it, even though the master theorem won't give it to us. Okay? So that's recursive algorithms, recursive relations for them. Now let's prove that this is correct, because that's something that we really care about doing as computer scientists. We want to prove that our algorithms, whatever we wrote, was correct. So let's take this algorithm, and here's our theorem, right? We'll prove it using recursion, or sorry, induction. We will use induction to prove that our recursion is correct. So our theorem statement looks like this. It's for all n, for all calls to factorial, for all n, fact of n is equal to the real factorial. It returns. Fact of n returns n factorial. That's kind of what I want to say there. And so this is my predicate. This is my p of n. Yeah? And so our base case, I guess n greater than or equal to 0 is what we want to really say here. My base case then is p of 0. I need to show that, well, plug in 0 for p of n, plug in 0 for n. I need to show that fact of 0 better return the real result of 0 factorial. And what do you know? This returns 1. This answer is 1. 1, 1, checks out. Cool. Then we have our inductive step. We got to show that fact of k plus 1 is equal to k plus 1 factorial under the assumption, right? We assume p of k, prove p of k plus 1, right? So assume p of k is true. Assume fact, this is our inductive hypothesis, assume fact of k is equal to the real k factorial. It returns it properly there. And then what we need to show, based on that, is that fact of k plus 1, one more, is really going to return k plus 1 factorial. Yeah? So, this is how we do it. So what does fact of k plus 1 return? Well, it returns whatever n times fact of n minus 1 returns. So it returns k plus 1, because I'm calling it with k plus 1, k plus 1 times fact of just k, right? Because that's n minus 1. It's just k. And now, what do you know? I have this. I have it in my hypothesis as well. I can unfold it. So fact of k I get to assume is just k factorial. I assume that the recursive call is doing the right thing. So this expands to k plus 1 times k factorial. And under the rules of factorial, right, you have all the numbers from k down to 1 multiplied. And if you add k plus 1 on top of it, that is all together taken to be k plus 1 factorial. It's going to compute k plus 1 factorial. And that is exactly what I needed to show. Fact of k plus 1 really does give me back k plus 1 factorial. That's beautiful. So that's QED. We have proven without a shadow of a doubt that for all n greater than or equal to 0, fact of n really does compute the proper factorial, proper mathematical factorial, and gives back that right answer. Go us. All right? Let's keep going. We got graphs now. So, sorry I'm going a bit fast. This is just a lot of bang for your buck. That's what I'm trying to give you here. So terminology for graphs, let's remember what they are. So you can have directed or undirected graphs. So you got your nodes, your vertices, your edges. Here is a directed graph where your edges have targets, right? Sources and targets. So you can go in this direction. You can have self-loops. This is a directed graph. There are arrows going here. And so we usually, or we always use directed graphs to represent relations, for example. You can totally have two arrows from the same source to the same target. It just seems weird. It's not normal, but possible. And then an undirected graph would look something like this. It's just the fact that an edge exists at all is what you care about. There is no directionality, right? That's the main difference. It's like boop, boop. You can have still parallel edges, that's fine, but again, there's no directionality. Boop, boop, boop. There's my graph. There's my undirected graph. So all the dots are vertices, places you can move around to. Edges are the things that connect them. The degree, you can talk about the degree of a node or a degree of the graph itself. Right? So the degree is how many outgoing edges you have. The degree is the number of neighbors. So, for example, so the degree of this node, for example, it's got 3 neighbors. So its degree would be 3. And you can also talk about the degree of the entire graph. You just sum up all the degrees of its nodes. You can get subgraphs. You can pick out part of the graph. Like, let's say I care about this node, this node, this node, and this edge and this edge. You pick out certain nodes and certain edges, and you make a subgraph. That becomes this. Boop, boop. Okay? That is a subgraph of this original graph. There's always an original graph that you're picking stuff out of. Okay? These are parallel edges. They're going same source and target, same direction if it's a directed graph. And finally, self loops. Makes the most sense with a directed graph, like you can come back around on yourself. You can technically have a self loop in an undirected graph, but it just looks extra weird. And normally we don't talk about them in undirected graphs like that. So yeah, that's all that. I think that the hardest stuff, the hardest terms to keep straight in your mind are absolutely walk, circuit, path, and cycle. I still have trouble. Don't you worry. So walk is the most generic. I'm trying to move through my graph. Let me use green again. So a walk is just, all right, I am moving around my graph. I'm following vertices and edges. Well, I guess I'll use the undirected one. I'm moving around my graph, following vertices and edges. I can come back around on myself as much as I want. Just remember to keep that in my write-up of where I've been. It's like I'm walking around. I'm moving between vertices and edges. A circuit is a walk, but you don't have any edges more than once. And you must there also come back to where you started. So you can visit the same node a bunch of times, boop, boop, but no edges more than once. So this would technically be a circuit, okay? Even though I came back to this node, I came back along a different edge. See that? So that's a circuit. Then we have paths, where you cannot have edges or vertices more than once. So that's the standard thing that we normally talk about. So boop, boop, boop. I'm forced to stop here, right, for this particular path. Because if I go anywhere else, I'm going to come back to a vertex. Or try to go along an edge I've already been along. Yeah? So path, no edge or vertex more than once. And then finally a cycle is a path up until the last thing. It's a path but the first and last vertices. We let them be the same. We're nice like that. So here's a cycle. It's a path up until here, but we want to close it off. Yeah? That's a cycle. So try and keep those straight. Look at the examples in your book, but that's the quick 2-minute explanation of all of those. Let's also talk about connectedness. So graphs can be connected, they can be disconnected. If there is some connectivity in them, you can talk about the connected components, even if the graph is not fully connected. This graph taken as a whole is connected. You can always get from any node to any other node. That's what it means to be connected. If you have a graph that is disconnected, that means there are pieces that can touch each other, that can get to each other. Like here is a piece of a graph. Here is the same part of the same graph, but now we're over here. Here is more stuff, more nodes, more edges. So consider this to be one big graph, right? Call this whole thing G. It's my graph G. You can have connected components now. So like all of these are connected to each other. So that's a connected component. All of these nodes are connected to each other. That's another connected component. And finally this one, okay? So it's just little pieces, little subgraphs, maximal subgraphs, we say, that are connected. And that's that terminology. And then we have regular graphs, cliques, and fancy KNMs that kind of like section off who's connected to who, or who's touching who. So let me give you some examples of those. A regular graph is a graph where everybody has the same degree. So here's a graph where everybody has degree 2, right? This one has 2. This is the final graph. This has 2 neighbors, and so does this one. They all have the same degree, same number of neighbors. That's a regular graph. Cliques, KN. Those are technically regular graphs, right? K4, for example. It's just everybody's connected to everybody else with a node. Or not with a node, with an edge. Like, here's this node. It has a way to get straight from itself to everybody else. So all those must exist. Degree 3 for everybody. And then like this one, it's got a way to get to everybody. So that one and that one. I guess the only one that's missing is this. So that's K4. That's a clique. Everybody is so close to everybody. They all touch each other. There's a way to get from every node to every other node with a single edge, along a single edge. And so this is by definition a regular graph. It's just a cooler one. Technically also regular. And then finally, we have graphs that look like this, KNM. This is when you have like two sections. So let me show you K34, for example. You have two sections of your graph. Here's 3 nodes, 3 vertices, and then here's 4 nodes. And this is similar to cliques, but the idea is that these nodes can't touch each other, these nodes can't touch each other, but every node here knows how to get to everybody else in the other section, the other half, and the other side immediately. So there's 4 edges here. Let me try and draw better lines for you. This one has a way to get to everybody on the other side immediately. 1, 2, 3, 4. So there's going to be 4 times 3 edges. 1, 2, 3, 4. There we go. So this is not a regular graph because everybody over here has 4 neighbors. Everybody over here has 3 neighbors. Okay? So that is K34. It's like you section them off into groups of 3 and 4, and then within a group they can't talk to each other, but they know how to get to everybody in the other group immediately. So that's K34, or in general, KNM. Alright, so that's some terminology. Once you have graphs, you care about representing them inside of a computer so that you can like figure out the shortest path. Like Google Maps has got a lot of graphs with streets and distances between them. So here is a example graph. Here's my example graph for us. We have 4 nodes, A, B, C, and D. And let's say there is an edge between A and C, an undirected graph, let's say. A and B are connected, and then B and C have an edge between them. And let's do B and D as well. So that is the graph itself, and we like to represent this inside of a computer. There are 2 standard ways of doing that. You can make an adjacency list that says for every node, like it's like a map from nodes to lists of other nodes, technically themselves if there's a self loop, but it's kind of like a hash table, where the keys are the nodes, and then you have a list of other nodes that you're connected to by an edge. So A has an edge to B and C, so we store in a list BC. Yeah. B is connected to A, C, and D, so we store in a list. From B, you could get to A, C, and D. C is connected to A and B by an edge, so we store that fact there. And then D is only connected to B by an edge, so we store it like that. So that is our adjacency list, and this is perfect information to tell us exactly what's going on, what edges exist in this graph. Okay? You can also do it with a matrix. And this does waste a little bit of space because you have to say if an edge is there or if it's not there. Whereas an adjacency list just says if it's there, I'm including it. Otherwise, assume it's not there. But for a matrix, you kind of like line up everybody, and then you consider where they overlap. It's like, it looks like this. Let me do my best at drawing things. Just like that. And so, do A and A, are they connected? Is there a self loop from A to A? No. But there is from B to A, from A to B, and from B to A. So from A, let's do from on this side and 2 on this side. So from A to B, there is an edge, and also from B to A, there's an edge, because it's undirected. So BA also has a 1 here. 0 if it's not there. It's like true and false, right? And then same for A and C, so there's a way to go from A to C. Oops. That's just a 1. And there's a way to go from C to A, same edge. And same for B to C, B to C, C to B. and B to D. B to D, D to B. And I believe that is the only, those are the only things. So there are 1, 2, 3, 4 real edges, and we should see 8 things here because it's you go in both directions. 2, 4, 6, 8. So I think that's right. And zeros everywhere else to represent the idea that there are no edges in those directions. Those do not exist. All right. Even fancier graphs. Let's talk about Euler circuits and Hamiltonian cycles and paths. So a Hamiltonian cycle or a path is a cycle or a path that goes through every vertex in the graph. All right. So for example, let's start with K4. Here's my graph. There is a Hamiltonian path in this graph that looks like this, right? Just go here, then go here, and follow this edge, and this edge, and then this edge, and that's a Hamiltonian path. You can also make it a Hamiltonian cycle and go back to the start. See that? So that exists, that's a thing. So let me just color those in better. So Hamiltonian cycle or path. And then Euler circuits are circuits containing every vertex and path. And we're careful to say circuit, right? Because you can duplicate nodes along a circuit. You can duplicate vertices. But you can't duplicate vertices along a path. See that? So my fun favorite example, if I can remember how, is this little box. So here's my graph. There is an Euler circuit in this, and I do not remember how, but we'll see if I can remember. Something like this. Boop, 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 boop. Nope, did it backwards. Is it like this? Yeah. Boop, boop, boop. I'll never remember it, but at least I found it. So that was me visiting every vertex and, sorry, I should say edge here. Sorry. Every vertex and edge. Excuse me. Every vertex and edge. That's an Euler circuit. Okay. And then the next thing that we studied were trees. So let's talk about those. And of course we have to include Bob Ross. Happy little trees. So tree terminology, what do we got? New from CSCI 841 is free trees. You do not have to specify a root of a tree. Just trees look like this. You have children. There's one way to get from every node to every other node. So here's a tree that has no root, right? But it's still technically a tree, according to the tree definition. You can root that tree by picking somebody and saying that this is the root. Okay? That's how that works. Now we have to talk about levels of rooted trees. We have all these fancy terms. And let's get started. Most of these terms come from rooted trees, at least. So here is my tree. Boop. 2 children from the root. Let's say that this node has 3 children. You're totally allowed to have more than 2 children. It's just called a binary tree when there's at most 2. We don't need just binary trees. We're cooler than that. So here is my tree. You can talk about the level at which things are. So the root is at level 0, and then you go down successively from there. So this is level 0. This is level 1, level 2, level 3. The height of the tree is the maximum level that exists, so the height of this tree would be 3, thanks to that node. Parents and child relationships, it's always you go back up to get to your parent, you go down to get to your children. So this node has 3 children, right? These 3 nodes. And everybody only has 1 parent. Like this node has 1 parent, it's this guy. Has a grandparent, this guy. Okay? And just in general, an ancestor is somewhere up the tree. So here is all the ancestors of this bottommost node. It's this one, its parent, its grandparent, its great-grandparent. Those are all your ancestors. Okay? And then on the flip side, you have descendants. So every node is a descendant of the root, right? Because you go down to get to them. this node, for example, it has 3 descendants. This guy, and this guy. It's children, it's children's children. It's all just like a family tree. Leaves do not have any children, so there are 1, 2, 3, 4, 5 leaves in this tree. A leaf in a free tree is kind of weird. It's just any node that only has one thing it's connected to, because there is no root. Things look a bit weirder. So a leaf in a free tree, it's just if you have one degree 1 node. And then finally a subtree is, well, make a tree out of vertices of another tree. So pick a starting vertex, make that the root, for example. You could have also a free tree with a subtree in it, but let me pick out a subtree of this rooted tree, for example. Just say, like, all right, this node is going to be the new root, and so consider the tree made up of just it and everybody that it's connected to. So this is a subtree. Whee! See that? So there are 2 subtrees of the original root. It's that guy and that guy. But it's just a subtree. It's like, all right, this is the new root. Pretend it's the whole tree now. That's all that is. Subtree. We also have traversals for trees. Those are fun. Pre-order and post-order. In order, which only works for binary trees. And then breadth first search. So let me show all this to you. Here's my example tree. I'll have this tree. It's not the hardest one to do stuff on. It's going to be kind of small. So I'll have these vertices and edges. So A, B, C, D, E. I'll name them like this. And so let's do pre-order and post-order. These are recursive algorithms. It's always, in terms of pre and post mean, pre and post and in, by the way, mean in which order do we visit the root. Pre means first, right? So it's root, then recursively visit your children. And post means we visit the root last, so children first, then root. Okay? And then in order, it's when it's a binary tree, you have a left and a right only. That's your root is in between the left and the right. So it's left, recursively visit the root, then recursively visit the right. Okay? So let's do this for pre-order. So for pre-order, it's always root. This is the root of the tree, by the way. It's always root, then children. So for pre-order, the very first thing we visit is the root of the whole tree, and then we recursively visit the left subtree and the right subtree. So it's the left subtree first. It's always root, then children. So B gets visited first, then we visit D and E recursively. So it's going to end up being B, D, E, right? Then we're done with the left subtree. We're ready to recursively visit the right subtree. Just the other one. The other child, the next child in order. If we had more than 2 children. Okay, so the next one's C. And I hope that makes sense. That's pre-order. Post-order is kind of the opposite. It's always children first, then the root. So start at the root, but we got to visit recursively the children first. Recursively visit the left subtree, recursively visit the right subtree, visit A last. You can think of it that way. Like the last thing we see is going to be A in the post-order traversal. So it's B, D, E, then it's recursively visit left, then right, then your root. Okay, so it's going to see D, E, B first. Then we recursively visit the right of the root. So recursively visit left, right, there's nobody, and then the root itself, so C. And so now we visited left and right, ready for the root. That's A. So that's post order. And then breadth first search is nice. It's just the level order. Gosh, do I want to show you in order right now? In order really only makes sense when it's like a breadth, or a binary search tree. But I guess I could show you in order. Why not? It's always left, root, right. So left, root, right. Okay, so recursively visit this one. And again, it's left, root, right. So D, B, E. So now I'm done with all this. Then root, A. Then right, C. And finally, BFS. That's the easy one. It's just in order. Boop, boop, boop. Level order. So finally, this is easy to read off. It's just A, B, C, D. Okay. So those are my traversals. those are traversals on trees. You can also have traversals on graphs. So don't forget about those. What do those look like? Let me give you a graph. Let me draw a sample graph. Here's my sample graph. It'll be undirected. Easier that way. So we have A, B, I don't know, just for fun, C, D, then E over here. So that's my graph, and I'm going to do DFS, depth first search on graphs, and breadth first search. So I'll draw it twice. So depth first search is essentially post order. It's essentially post order for graphs, so let me try and explain it to you as we do it. So there's always a starting vertex and an order in which we visit things. These traversals are really exploring the tree and not doing any extra work. So it's going to make or exploring the graph and not doing any extra work. So they make a little sub-tree out of the graph. So they don't want to go back along to a node that they've already visited. That would make a cycle. Trees can't have cycles, right? So it's naturally going to form a tree here. And let's say we start at A. That's the first node that we visit. Then let's visit the other nodes in order, depth first, right? So recursively visit everybody else in order. Kind of like post order, add to the stack kind of thing. But you do process before, so maybe I should be saying pre-order for graphs. But you really are getting to the bottom, so I guess you could talk about it either way, but let me show you how depth first would work here. So it's go as deep as you can. So B and E are options. Let's take the alphabetical order. So I'm going to push B to my stack, and that's the next thing I'm going to follow. So I'm going to follow this edge to get to B. That's the second thing I see. And then I'm going to go and be like, all right, I can go to A from B or to E. Well, I've already been along that edge. I've already been to A. I'm not going to go there anymore. So then it's going to choose this edge. I'm going to go to E. That's the third thing that it sees. And then I could go to A or to D. It'll pick the one it hasn't seen yet to make a tree, right? So it goes to D fourth, and then finally C last, fifth. And so it draws this little, it's really just a path, but it's technically a tree. It makes a tree out of its traversal. So that's DFS if you assume that you're going to pick the lower in alphabet node next. And then BFS is go as wide as you can first. So for example, A can go to B and E, and we haven't been either of those places yet. So A is the first thing we go to, and then B and E, those are 2 and 3. We go to both of them at the same time, kind of. And then we look at B and like, have I been to all of my neighbors? Yes, I've been to A, I've been to E, so don't consider that one. And then E goes to all of its neighbors that are unseen. So it's going to D, that's 4, and then D goes to C is 5. So it's going as wide as possible at the start, whereas DFS is going as deep as possible at the start and throughout. Okay? So those are the orders in which we visit those nodes for DFS and BFS. Definitely take a look at my previous examples and all the cool animations in the book for more on that, but that is as much as I want to say about graphs and trees and fancy induction and recursion. So that's the first part of the review. That'll be our first lecture, and next time, in the next lecture for this week, we'll come back and do counting and probability, and that'll be it. Alright, so I'll see you in the next one.